Okay, so we're starting exploring graphs of sinusoidal functions. And our goal to start is to investigate the characteristics of the graph of sine functions. So normally we start this with a bit of an exploration, meaning I would give you some physical things that you would actually rotate to map out and explore the what happens when something moves in a circular way. So in the investigation, we simulate the motion of a Ferris wheel. We have a circular object, and I would be giving you a cutout of a little Ferris wheel that you would rotate, starting with the rider at the bottom. So if this is the pathway of the Ferris wheel, the rider starts, we have his little seat here at the bottom, and he rotates up and around the Ferris wheel. As he does so, we're recording various distances from the floor or the ground to see how far away from the ground the rider will be at certain points in his journey. So first we go 90 degrees, then we rotate further and another 90 degrees so that we're at 180, then again so that we are at 270, and then back down so that we're at 360. So in effect making a full rotation like you would in a Ferris wheel. At each of those key points, we have a measurement from the ground. So we're repeating and we're rotating around until the Ferris wheel's at the bottom again. If you want to just take a circular object and mark it and see what happens, you can kind of see the relationship. There's also a few different simulators of Ferris wheels online, but the idea is that you are tracking the movement as the Ferris wheel goes around and the distance around. Now we've only got 4 points that we're looking at, but that's enough. Now here it says record the radius of the circular object. So it's a little challenging because it's going to depend on your actual object, right? And here, it's hard to do because I expanded it so that I could get, so that this would be 6 centimeters. So let's see. 1, 2, 3, 4, 5, 6. So I need to make it a little smaller. 1, 2, 3, 4, 5, 6. Tiny bit smaller. No, a tiny bit bigger. Around there. So this should be in effect. So our radius would be half of the distance across this object. 1, 2, 3, 4, 5, 6, 7, 8. So we would say that the radius would be half of that, right? So if the diameter is 8, the radius of this object would be 4 centimeters. Okay, it's good to have that kind of measurement. So that's exploring. Now, like I said, I expanded it, so it's a little bit of an approximation because as I expanded it, certain measurements got a little off, okay? But we're close, okay? Now, the big thing is to look at what happens to the motion and what happens as we rotate through that 360, what happens. So if we do our rotations, time in minutes, we start at 0. And if we look back at our picture at 0, we're at 2.5 centimeters, which is equivalent of, we're not going to say 1 foot, we're going to actually say 1 meter, okay, because we're in Canada. At 2 minutes, we'll be at 90 degrees, and if we look back, that was at 6 centimeters, which is equivalent to 1 meter. At 180, we're at 180 degrees, this time would be 4 minutes. This is a pretty slow-moving Ferris wheel. And looking at our sketch, we're at 9.5 centimeters. At 6, we're at 270, and again, we're at 6 centimeters. And at 360 degrees, it's at 8 minutes, takes 8 minutes to rotate through, and we get 2.5 centimeters. Now what we want to do is we want to plot that out on a grid, but we're going to plot time versus height. So plotting time versus height, we're going to look at what happens. So let's make, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we go up by 1, remember we changed this to meters, not feet. Time in minutes. So we're just going to track time versus our height. So at 0, we are at 2.5. And this is at the bottom, right? We haven't moved at all, so we're at the bottom. Then at 2 minutes, we move up to 6 meters. Okay? And that's at the center of the circle. At 4 minutes, we reach 9.5, which is at the top. And then at 6 minutes, we're at the center again. Okay, and then at 8, we come down to the bottom. Now you notice the bottom doesn't go down to 0 because if you've ever seen a Ferris wheel, well, you don't sit on the floor, right? You're always elevated a little bit above the ground. There's probably a little ladder to climb up to get in if it's at 2.5 meters. So right there would be our bottom again. Then we can kind of connect these. Now it's going to be a curve, and I'm not the best curve drawer. I kind of want to do that over. You would never tell that I'm actually an artist. And then we can kind of predict what would happen if we went on another rotation. Well, 2 minutes after that point, we would probably hit the center again. Then 4 minutes after that point, we would hit the top, which is at 9.5. Then another 2 more minutes, we would hit here. And then at 16 minutes, we would have the end of our ride. We'd be back at the bottom. So we can connect those. And again, I really want to redo that line because it looks so gross. Okay, so better. Okay, so center, top, center, bottom, and this is likely the end of our ride, right? Okay, so we've basically done 2, which says extend it through an additional rotation. This was the first rotation, and this was the second rotation of the Ferris wheel. Okay, so it gives us an idea of what that is. And basically we're graphing the distance that Ferris wheel height is from the ground, okay, as above. Okay, now on the graph, I've kind of done this. The rider gets on the Ferris wheel. That's at the bottom, right? The next point says at the top of the Ferris wheel. That's where we've labeled our T's. Then we have the rider is at the same height as the center, so that's where those C's are. And the rider gets off at the end. Okay, so we can also call that E. So I've done basically 3 when I graphed it as well, as above, right? It's easier than scrolling back and forth. State the following and label them on the graph. The distance of the top of the Ferris wheel to the ground. Well, when it's at the top, if we look at our chart, it's at 9.5 meters, right? The distance from the center of the Ferris wheel to the ground. Well, it was at 6 meters. The distance from the bottom of the Ferris wheel to the ground. Well, it was at 2.5 meters. And then the radius of the Ferris wheel. Well, we found that out before. And we can kind of figure that out. 9.5 minus 2.5. I think my measurement was off. Because 9.5 minus 2.5, right? That's top to bottom. Is 7. 7 divided by 2 is 3.5. Now, bear in mind, I was dealing with a ruler on here that as I moved it and changed size, it's probably had a little bit of an impact there, right? Now, predict how the graph would change if the Ferris wheel were larger. So right now we're dealing with one that's this size. If it were larger, but it starts at the same height, then we're going to see a difference. So let's see. We're going to map out our grid. So if we have and right? So that would be our initial one, is going like this, right? If it were larger, that would mean that it would start at the same height, but it would go higher and then down, and then higher and then down, because the top height would be higher, but it still would be the same height at the bottom, right? So the black is the original, and the red is the new, okay? So if it were higher, we would just have a higher curve in our sketch. Predict how the graph would change if the Ferris wheel were closer to the ground. So let's think about that. So we have our sketch. So our original kind of looks like this. Okay. If it were closer to the ground, so our original looks like this and the ground is there. If we moved it closer to the ground, that means that it would start lower, but it would kind of have exactly the same trend. It just wouldn't go as high because it started lower, right? So that means the top would be, there should be an equidistance here and here and here and here. That should all be the same distance, and it would be lower, okay? Predict how the graph would change if the Ferris wheel were rotated faster. So this was time, right, versus height. So let's sketch that out. So I've got so we're now rotating it faster. So let's start with our first sketch. Oh, isn't that beautiful? If we're rotating faster, we're going to hit that height and the bottom faster, right? So basically the curve would be more condensed. And the faster we go, we're still going to hit the same heights. We're just going to have more rotations. So the black is original. The red is faster. And the blue is even faster, right? Because we're just going to get there more, so we'll have more cycles. Now, of course, my sketches look pretty crappy, and it's kind of nice that we have technology that's going to help us make it look much more beautiful than my sketches look, right? Yes, trust me. Okay, let's ditch that ruler. Okay, and we're going to move it up. Now it says a Ferris wheel has a radius of 50 feet and riders get on the bottom of the wheel 10 feet above the ground. It takes 4 minutes for the Ferris wheel to make one complete revolution. Sketch a graph showing the height of the rider during 2 revolutions of the Ferris wheel. So, using what we know. All right, let's draw a picture first of our wheel, because that will help. So if we have our wheel, and it's got a radius of 50 feet, and the wheel is 10 feet off the ground. Okay, that means the top up here will be at 60 feet, right? This side here will be half of 50 plus 10. So half of 50 is 25, so this will be at 35 feet because it's 25 plus 10, right? Okay, so we kind of need to know that for our rate. Now, on the bottom, we're going to have time. and it's in minutes, right? And our height, oh, wait a minute, it's the radius. Sorry, the radius is 50 feet. So that means, that means, dun, 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 this is 100 feet. So that means that this is 110 feet. And halfway up will be 50 plus 10. So it'll be 60 feet. That's a big mistake. So I'm glad I corrected that. So for height, and we'll keep the feet even though we're in Canada. We're going to put our time in. So 0, and then 2, and then 4, and then 6, and then 8. 0 to 4 is one rotation. So this would be 1, 3, 5, 7 minutes. Going up, we need to get to 100. So we go 20, 40, 60, 80, 100. So let's map this out. At 0 minutes, according to this, we're at 10 feet. So 0 will start right there. 1 minute, we're going to be at 60 feet because that's at the center point. 2 minutes, we'll be at the top, so we'll be at 100. Then at 3 minutes, back to 60. Then for 4 minutes, we'll be back at the bottom. We'll go up again to 60, then up to 100. Oh, wait, no, it's 110. I've got to change those dots. You're probably saying, Mrs. Finley, 110. I was looking at it going, it doesn't look right. 110. And then we go back down to 60, and then back down to 8. And we would draw a nice gentle, and it's a curve, so it curves at the top and the bottom. And that would be the sketch of our curve. Okay? Now, as you notice, the curve in the second half and during the second revolution looks, well, pretty much like the first revolution. And so what we're getting is this repeated pattern. And if we did more revolutions, we would get more repeated patterns, okay? What that is, so we're talking about a periodic function. And it's a function whose graph looks like waves, okay? That repeat in regular intervals or cycles. Everyday occurrences such as ocean tides, heights of the hand on a clock as a function of time, the height of a rider on a Ferris wheel as a function of time, or anything that repeats in a circular motion at a constant speed. Phases of the moon, they all show periodic behavior. And we use y equals sine x and y equals cos x as examples of periodic functions called sinusoidal functions. Now, a sinusoidal function is a periodic function whose graph has the same shape as y is equal to sine x. Okay? Graphs of sinusoidal functions have many characteristics that we're going to explore. Things like the number of x-intercepts, the value of the x-intercepts, value of the y-intercepts, domain, range, equation of the midline, amplitude, and period. And you're saying, what are all those things? Well, we're going to explore that. This is a nice little sketch that kind of shows you a lot of those things. If we have our sinusoidal function graphed, the midline, exactly like it sounds, it goes through the middle, so it's halfway between the top and the bottom of the peaks. The peak and the valley of that function. The amplitude is the distance from that midline to the top. The period is from one peak to another. So, and the maximum value would be the value at the top of a peak. The minimum value would be the value at the bottom of the peak. So that's a nice little sketch, just to kind of map it out. We are going to talk about these characteristics, and we're going to do some exploration of them as well. So never fear, it's going to happen. So here we have nice little definitions. Characteristic definition and the formula, how you find it. So the first one is the equation of the midline or the median. And that's what, as I said, it's a line that is halfway between the maximum and minimum values. So if we look on this graph, it's this red line across the middle. And the formula, if you add the maximum plus the minimum and divide by 2, you will get your midline. The amplitude is the distance from the midline to either the max or the minimum. It's going to be the same. It's always expressed as a positive number. Okay? And amplitude, very similar formula, but it is different. If you take the maximum and you subtract the minimum and divide by 2, you will get your amplitude. Period. Period is the length of the domain, that's our x value, our independent variable, that it takes to complete one cycle or pattern of the graph. There's several ways you can calculate it. Two of the formulas are: period is equal to the max x value minus the previous max x value, or you can take two minimum values. So if you only have a partial sketch and it goes from minimum to minimum, you can use the two minimums. But you're always going from either a max to a max or a minimum to a minimum. Alrighty? The size of an angle can be measured using degrees. A radian is an alternate way to measure the size of an angle. 1 radian is approximately 60 degrees. And we'll say it's also, we can say it's worth 2 pi. So if you think about that, 2 pi is going to be 6.28, right? But it's a slightly different measurement, okay? So just keep that in mind when we're doing this, okay? Maybe even forget I said that. An advantage to using radians is to measure angles that it allows you to express the angle measure using real numbers without units. An angle measure written without units is in radians, not in degrees. Okay? Now, it will come up when we're using radians that you might have to use a different mode on your calculator, so please keep that in mind. Okay. Describing the characteristic of a periodic function using a graph. Okay. Students in Simon's graduating class went on an exchange trip to China. That sounds like fun. While they were there, they rode the Star of Nanchang, which is one of the tallest Ferris wheels in the world. Simon graphed the periodic function that represented this ride. So this is the map of his ride. How can you tell that the lowest part of the Ferris wheel is 2 meters off the ground? Well, what we can look at is we can look at our minimum values. So here, our minimum values all happen at y equals 2. Look at minimums. Minimum values. They're all at y equals 2, right? And the height is in meters, so the minimum y value is at 2 meters, okay? Determine the maximum value of the graph. What is the height of the Ferris wheel? Well, the max is equal to 160. So it's going to be 160 minus 2, so it'll be 158 meters. Because remember, it's 2 meters off the ground. So you have to subtract those 2 meters. Determine the equation of the midline. What does this value represent? So remember, midline, y is equal to max plus min divided by 2. So it's 160 plus 2 divided by 2, which is equal to 81. And what does that mean? What does that equal? Well, it's the center height of the Ferris wheel. And if we scroll up and we can look, So that would be right here. That would be where our midline is, so it's y is equal to 81. That would be our center height. So that's representing our center height of our Ferris wheel. Determine the amplitude of graph. What does this represent? Well, the amplitude is y is equal to the max minus the min over 2. So that's 158 divided by, or let's write it all out. I kind of shortcutted in my notes. 160 minus 2 over 2, so it's 158 divided by 2, which is equal to 79. That equals the radius of the Ferris wheel. So if we look at this on our map, on our graph, from here to here is equal to 79 meters, and from here to here equals 79 meters. Okay? Alrighty. So that's a little bit of an exploration there of that particular Ferris wheel. There's other situations, however, where we have sinusoidal functions and where we can use these measurements and calculations. For a physics project, Morgan swung on a swing. Lily used a motion detector to measure Morgan's height above the ground over time. As she swung back and forth, so that she's measuring the height, right? The girls then switched tasks in order to collect a different data set. Lily swung on a different swing, and Morgan collected the data. So each swing is going to have a different length of chains, so it's going to be a different height off the ground, and also each girl is going to swing at a different rate. Okay? The girls graphed their results in two different graphs as shown below. At the end of each cycle, the swing returned to its initial position, which resulted in the sinusoidal graphs. Okay, so we have our two graphs here. So we're going to compare these, right? So looking at these, let's think about the things we're looking at. For the period, if we compare these two, Morgan, her period goes from 0 to 2. Right, that's our period, 2. Lily's goes from 0. Oh, sorry, no, this isn't 2, that's 1.5. I got to read my graph right. So Morgan's goes from 0 to 1.5, where Lily's goes from 0 to 2. So Lily has a longer period. Remember, periods is from amplitude to amplitude. Looking at it goes from maximum to maximum, right? Looking at amplitude. So amplitude, for our amplitude, we're looking from our midline all the way up. We actually probably should do midline first, right? Because midline goes from here to the top. So our midline is going to be 2 minus, so it's like 1, 2, 3, 4 3/4. So 4. So it's somewhere in the middle of here, right? And Lily goes from about 0.75 all the way up to 2.5. So Lily's is up here. So for the midline, Lily has a higher midline, okay? It's a little bit above, and you've got to actually look at them very carefully because they don't match up exactly in terms of the size of the graph, so you've got to count the squares. Amplitude, Lily also has a bigger amplitude, right? Because it's this distance here. So whereas Morgan's is like 2 and a bit, Lily's is 3 and a bit, okay? So we've got some different data there if we compare it. And now we're going to answer some questions. It says, who swung higher? How do you know? Well, Lily, if you look at the height of her swing, not only did they both started at about the same height, but if you look, her amplitude is bigger. So Lily swung higher. Okay. Who swung faster? Well, from the period for Morgan's is smaller than Lily's. So that meant it took her less time to get from her max to her max. So Morgan, because her period was shorter. So it means she was going faster, not as high, but faster going up and down, right? Determine the height above the ground on each swing at 4 seconds. So if we go back here, and remember, they have different periods and different amplitudes, so we have to look at each one. So at 4 seconds, Morgan's is about at 1 meter. And at 4 seconds, Lily's actually at the crest. So she's at 2.5, right? Like it's way up here at the top, right? So the height of each swing, Morgan is at 1 meters and Lily is at 2.5 meters. And that's, it has more to do with the fact that they're at a totally different point in the cycle of that repeat periodic function. Okay. Also, Lily does go higher, so that helps too. Okay. Alrighty. Describing the graph of a sinusoidal function in degree measure. Okay. So if we look at this and we want to know what is the period of the graph, well, the period goes from crest to crest, right? So if we start at 0 and we go to the top, we can do either minimums to minimums or max to max. Either way doesn't work, or will work. I'm doing minimums to minimums because it starts at 0, right? Now, each of these is 60 degrees, right? So that means that this is at 180 if we sketch it in. So the period of the graph is 180 degrees. Then it says, find the maximum and minimum values. So the maximum value is right there. I'm going to do it in a different color so it's easier to see. So this would be our maximum, which is, looking at our growth, which is 7. And our minimum over here is -3. Okay? So maximum is 7, minimum is -3. Using the maximum minimum values only, determine the range, the equation of the midline, and the amplitude. So the range is our y values, right? Well, y would be greater than or equal to -3, and it would be less than or equal to 7. Not y, 7. Why did Mrs. Finley write that? I don't know. And y is in the set of real numbers with those limitations. The midline is max plus min divided by 2. So that's 7 plus -3 divided by 2. So our midline equals y equals 2. Okay? And then our amplitude. We've got enough to do it. Amplitude, very similar. It's max minus min over 2. So 7 minus a -3 over 2. Well, minus a negative is plus a positive, so, and it's not a y equals, it is just a number. So it would be 5. Okay, so our amplitude is 5. So what that means is that if we sketched in our midline, which is at y equals 2, then the distance from the max to the midline would be equal to 5. Okay, so this is y equals 2, and this would be our amplitude. Okay, sorry my drawings get a little sketchy. I should really increase the size of the page so you can see it clearer. Okay, describing the graph of a sinusoidal function in a radian measure. So we just did it in degrees. Now we're going to look in terms of radians. Now if you can see there, we don't have any degrees on our chart. We're describing this in terms of radians. So what is the period of the graph? So half a period is 2.5. How do I know that? Well, let's take a look. I'm going to go from max to min. Max is right there, and min is right here. Okay? I don't have two maximums, and I don't have two minimums, right? So but I do have a max and a min. So that's where I'm getting half a period goes from 1.25 to 3.75, which is equal to 2.5. So that means a period would be 2 times that, which would be 5. Because it's not in degrees, we would say this would be 5 rad. Okay. Now, because we don't have 2 maxes and 2 mins, or 2 mins, we have to look at what half a period is, because a period goes from crest to crest, right? Find the maximum and minimum values. Well, my maximum value is right there, which is 2, and my minimum value right there is -4. So maximum is 2, and minimum is -4. Okay? Pretty straightforward. Using the max and minimum values only, determine the range, the equation of the midline, and the amplitude. So our range, which is our y values, goes from -4, y is greater than or equal to -4, and less than or equal to 2, and y is in the set of real numbers. Okay, so that's my range. My midline, thinking about our formula, it's, I want to write out the formula because I like to do that at this point. So our midline is max plus min divided by 2. So that is equal to 2 plus -4 divided by 2, which is -1. So y equals -1. And if we look at that, -1 is right here. So that would be our midline. Okay. Then looking at the last thing it wants us to find is the amplitude. Amplitude. And again, amplitude, write out the formula, max minus min divided by 2. So that's 2 minus a -4 over 2. So that is equal to, minus a negative becomes plus a positive, so it's 6 over 2, which is 3. And if we take a look at that, if we go from the peak to the midline, this distance here equals 3, and that is our amplitude. Okay. Groovy. Almost done here. More information. Now, one of the easiest ways to understand radians is to compare them to their degree measurements. So, Angle degrees, angle radians. 360 equals 2 pi, right? We know that, right? 180, therefore, would equal pi, because it's half. 270, well, 270 is halfway in between, so we can write that as 3 over 2 pi, right? Now, 2 pi is approximately 6.28. 3 halves pi, 1.5 pi, is approximately 4.71. Pi is approximately 3.14. 90 degrees would be pi over 2, so it's half a pi, which would be 1. Almost there. Sorry about that. I did it again. Exactly the same spot. 1.57. So important to remember from this, 180 degrees is equal to pi, and 360 equals 2 pi. If you remember that, you should be able to remember your radians. Okay? So if you just compare 180 degrees to pi, or right, then you're good. Okay? Because that's 360. Okay. Graph the function of y equals sine x. For degrees, use the window settings. So we're going to do this on our calculator. Looking at your calculator, first set up your windows. So it gives your windows there. So we're going to put in 0 for our x max, 720 for our x min, and 60 for our x scalar, xcl. Okay. Y, we're going to put in -2 for our y min, 2 for our y max, and 1 for our y scalar. So this is our windows, right? Our window settings. Okay. And we're going to do it first with degrees, and then we'll go back and do it for radians. So let's do it with degrees first. So we've got those in. So you're going to put this for your y equals. So y equals, and you're just going to put in sine of x, and you're going to hit graph. Now you should get a beautiful little graph happening here. When you graph it, I need to put it on here. I'm going to actually do it in red, so I'm going to match it up. Here and then it crosses at 180, and it crosses at 360, 540, and 720. My amplitude is 1, and it's halfway between there and there. My -1, 1, -1, 1. Okay, so let's sketch this. And it should be a little more curvy than I've done. I apologize for that. Now let's do the radians. Okay, for radians we have to change a couple of things. So we've got to change our window settings. Okay, for radians we're going to put in as follows. We also need to change our mode, right? So you can see the mode button. Mode button, you're going to go down and you're going to put it in radians. Then you're going to change this window. So our x minimum will be 0. Our x max will be 4 pi. Our x scalar will be pi divided by 3. And you can see when you put that in your windows, it does the conversion for you. The y is exactly the same, and we can leave our expression the same, right? When we put it in y equals, we don't have to change that. Then you hit graph, and you're going to get your graph of your function. So now let's graph this in. So what you notice is, starts there. We have pi, 2 pi, 3 pi, 4 pi. It goes up to 1 in the middle, -1 in the middle, 1 in the middle, -1 in the middle, and here. Wow, it looks very similar. Okay, so let's fill this out for the rest of it. So, looking at this as our baseline for our amplitude, for degrees, our amplitude goes from the midline to the top, right? So it's 1. Our period goes from crest to crest. So it's 360 degrees. The equation of the midline is y equals 0, right? The domain for the entire function, so this is the x values, is x is in the set of reals. The range goes from -1 to 1, and y is in the set of reals. And the y-intercept, it only crosses at the beginning at 0. Okay? Now, what happens with the other one? Slightly different. Amplitude is still 1. Our period from crest to crest is 2 pi. Remember, we said that those are equivalent. Equation of the midline, y is equal to 0. The domain, x is in the reals. Our range, very similar. In fact, it's identical. And our y-intercept is 0. Describe the relationships among the range, midline, and the amplitude of each graph. Okay, well, looking at them, they are the same. Okay, the only thing that's different is the period, right? So that is the only thing that is different. Okay. Example 6, sketching the graph of a sinusoidal function with the following characteristics. So now that we have this, we can take characteristics and we can work backwards. So it says the domain is x is greater than or equal to 0 and less than or equal to 360 degrees. Okay, and x is in the set of the reals. The range, y goes from, so let's map this out. It goes from -5 to 9. Okay, so we know our top and our bottom. The period is 120 degrees, so our crests are going to be 120 degrees, and the y-intercept is 2. So that means we start at 2, okay? Now the period is 120, so that means that we're going to see a repetition by the time we hit 120 of that much, okay? So if this is our peak, we're going to go up to our peak and down, and then our minimum is down here, and then we go here. Now you're saying, well, how do I know that works? Well, let's continue and just double check. So we would go here. We're basically hitting each time, right? So let's check. From peak to peak is 120 degrees, okay? So let's just map these out. I am not the best sinusoidal wave drawer. So we would go down, and we have to continue this all the way to 360, and then it ends because of our domain, right? So let's take a look at what we have just to make sure it all works. Our midline, right there, that's our midline. Y equals 2, right? What else do we know? We know our period was 120 degrees. We know that we're going from -5 to 9, right? Our amplitude, therefore, goes here. So our amplitude is 9 minus 2, so it is 7. Okay, A equals 7. And our midline is Y equals 2. And our period is 120 degrees. Okay, now I can redraw this way prettier just because it'll make me happier. I didn't mind it so much on this end, but I do want to redraw it because it just was making me cranky. And I didn't do that much better of a job, but oh well, what can you do? Some of it is taking those characteristics and mapping it out and thinking about what it's going to look like. Now, we've got lots in the need to know. We took in a lot of information today. This is actually a whole big page. So we're dealing with periodic functions, right? And it's a function whose graph looks like waves that repeat in regular intervals or cycles. And we're looking at the graphs of y equals sine x and y equals cos x, most particularly sine x. And they're examples of periodic functions called sinusoidal functions, but we will look at both. Okay? Sinusoidal function is a periodic function whose graph has the same shape as that of y equals sine of x. Now, the graph of y equals sine of x, and we looked at this, we looked at it with both radius and degrees, has the following characteristics. It's got multiple x-intercepts, one y-intercept. That's the domain. Here's our range. It's our amplitude. The period is 360 degrees or 2 pi radians, and the midline is defined by the equation y equals 0. So that's our y equals sine x. Now we also looked at a number of different sinusoidal functions, and we looked at finding their midlines. We used this formula here, and it's the median between the maximum and the minimum. We also looked at the amplitude, and the amplitude is the distance from the midline to a crest. And this is one formula we can use for it. Maximum minus minimum equals divided by 2. And the period is the length of the domain that it takes to complete one cycle or pattern of the graph. So you can either do it from maximum to maximum or minimum to minimum, whichever one you have. In some cases, you don't have the whole graph, so you might have to be able to find half a period and double it. We did that with one example. A radian is an alternative way to measure an angle. Size of an angle. 1 radian is approximately 60 degrees. An angle written without units is considered to be radians, not degrees. Remember, 360 degrees equals 2 pi for radian. 180 degrees equals pi. So if you remember that, that's why it says approximately, not exactly. Okay? So that is the first lesson. Now you've got some practice to do. Enjoy.